Welcome everyone to another episode where we delve into geodesy and distinguished geodesists in the world. My name is Mehdi Eshab, and today we have the privilege of sitting down with a well-known space geodesist and one of the pioneers of satellite altimetry, Anny Cazenave from the Space Agency. Professor Cazenave has made significant contributions to space geodesy, satellite altimetry, satellite gravimetry, and solid Earth geophysics. Please join us as we explore her career, insights, and how her research has affected our knowledge in the field. Welcome, Professor Kazanov, and thank you very much that you accepted my invitation.
It's a pleasure for me.
Thank you very much. Professor, you have done a lot of work during these years, and at least I know you from your works. You have done a lot. But I think it would be very interesting that the audiences can hear from yourself your own journey to the subject and what was the main and key issues that kept you interested in this field.
That initially, when I was a student, I wanted to be an astronomer. But life has made that instead of looking at the sky, I've been studying planet Earth, which I never regretted, I have to say. So, after a PhD on the rotation of the Earth, I was recruited by the French Space Center called CNES, Centre National d'Études Spatiales. Long time ago, it was really the beginning of the Space Geodesy era. So at that time, my job, my work was to study the position of artificial satellite in space, using tracking, what we call tracking data. For example, satellite laser ranging, a technique that measures the distance between the satellite and station on Earth. But there are other techniques. So I started to work on that, and because the main force acting on satellite is the Earth's gravity field, I was interested in determining, modeling the Earth's gravity field, and after that, to use this observation of the Earth's gravity field to look into the internal structure of the Earth. That is because, as you know, we can the Earth's gravity field, at least at long wavelengths, is give information on currents, convective currents in the Earth's mantle, etc., etc. So for a number of years, I I worked on I would say solid Earth geophysics, and after some years, I decided to move to more to the surface, and the reason was that it's because of the launch about 30 years ago of the first high precision altimetry mission called Topex Poseidon, that was developed by CNES in France and NASA in the US to study the ocean. So I decided to change my research field to oceanography and climate, and now for about 25 years, I would say, I am working on sea level rise, climate change, etc. So this was my career in space geodesy.
Thank you very much. It was interesting to hear these things from you, as I already read them from the internet about you and your interest. I knew that.
Okay.
But Professor, what type of changes has you observed yourself? Of course, you said that you changed your own subject later
Yes.
but what type of changes have you observed in the field so
I,
far?
I, I will not talk about geodesy before the space era. because I was not there first of all, and it was before the, I would say, the 60s or 70s. Geodesy was mostly related to measure distance on Earth and local gravity, but what I would like to say is that at the beginning of the space era, my feeling, my opinion is that geodesy was mostly driven by technology, and um, and I can give you a number of examples that you already know. For example, I just mentioned tracking measurements between station on Earth and artificial satellites like satellite laser ranging. So this was developed to measure the position of the satellite in space. But from this, as I just explained, we could infer the internal structure of the Earth. So this was an example of technology-driven scientific application. Another example, well-known application, is the GPS system, which, as you know, was developed in the US for military application purposes, and has been further used by geodesists to measure deformation of the Earth, tectonic motion, etc., etc. Another example I would like to give is the first altimetry mission developed in the US, satellite altimetry mission, like Geo3 and Geosat, were have been launched for military applications. That is to know the low high wave, I would say, short wavelengths geoid anomalies for submarine navigation. But we as scientists use this data when they have been accessible for science. To derive the seafloor bathymetry, for example, this is just an example. And this product has been used for a large number of applications, as you know, for example, for in marine geophysics, for tectonic application, but also for economic application like fishing, oil and gas exploration, etc. So to me at the beginning really this was technology driven, but I think that since 2 or 3 decades now the situation has changed, and several missions proposed by geodesists have been developed for science to answer scientific questions. So I can just mention high precision satellite altimetry mission like Topex Poseidon to study, and its successors, the JSON satellite to measure the ocean circulation, and now we are measuring sea level rise. The GRACE space gravity mission to measure mass redistribution in the Earth system, etc. So this is my opinion on this topic.
Thank you very much. Thank you very much. That was really interesting to hear you. But Professor, what type of changes have you observed? Is it sensor technology or satellite technology that you have observed, or have you observed any theoretical changes or development also as well in that field?
Today, satellite geodesy or geodesy in general is a truly multidisciplinary research field with application in almost all geoscience area. Uh, so, so it's not only obviously this has been based on the new technology on one side, a new theory, but mostly since, as I said, since a few years or 2 or 3 decades, to answer new scientific questions. And today, geodesy is a tool for me, and its application are in all area of earth science: internal geophysical structure, marine geodesy, tectonic motion, monitoring of active seismic areas, as you know, volcanoes, deformation, but also oceanography, ocean currents, uh, water resources. We now use geodesy techniques or tools for extreme events, like for example, with recent with altimetry or space gravimetry, we can at least monitor extreme events like floods, droughts, etc. And with a lot of application, there is a lot of application in climate science. So it's a big evolution over time since if we go back 50 years ago, where we were just measuring the shape of the earth, the gravity field, the rotation of the earth. Now we can use geodetic techniques in all, almost, maybe not atmosphere. So there may be some application, some GPS application for atmospheric physics, but otherwise in all area of earth science. So it's incredible evolution, I would say.
Thank you very much. This was really interesting. Very interesting. Professor, how can we, these are the things that we have worked on it and we understand what exactly what we mean. But how can we uh, explain to people the importance of these subjects?
I think I am given quite often presentation to the general public. So in general, I don't talk about the technical aspect, because the technical aspect, the processing of the data, is my job. But what the general public uh, need to know is the application, scientific application, scientific and with societal in general, many societal impacts. So I think that we need to not be too technical, because this does not interest the general public, how we do our job, our cooking, etc. But we have to focus on the application, in particular on the societal application. And I already mentioned a few. For example, my current work is about measuring, precisely measuring sea level rise at global, regional, and even local scales. When I say local, that is along the world coastline. And I try to explain why it is important to measure sea level rise. It's just an example. First of all, because sea level is one of the best indicator of current climate change, because it, it responds to change in several components of the climate system, the ocean, continental waters, etc. Even change in the atmosphere. So this is one point. Another point is that we need to know how much sea level is rising in the coastal zones. And from that, we can improve the model used to predict future sea level rise at the coast. So this is an example. We have to focus on this application that interest the society in general. The other example is about water resources. With space gravimetry, we routinely measure change in water storage on land, and we can even monitor extreme events I mentioned previously, like floods, droughts, etc. And this is very important for example, this extreme event for agriculture, for water resource management, etc., etc. And this is what interests the general public, not the way we are processing the data, or computing, developing codes, and so on. This is our job, but people are not interested in that aspect, but on the applications.
Yes, yes, I 100% agree. 100% agree. We have to do it. More applications. People should see why we do these things at all.
And
Why? What?
explaining what we are doing has some impact on the society in general.
Also, what do you advise us as generation after you, with me, and the generations after me? What is your advice to us, younger generation?
It's difficult to it's difficult. So I would like to, first of all, as a young generation, why have you chosen geodesy as a research field? I don't know. Maybe it's just opportunities, etc. So I okay. So my advice would be, but this is general for science research. Work with passion, uh, pursuit excellence, and develop self-confidence in what you are doing. Be curious, and for geodesy in particular, don't stay locked up into a very narrow domain, because, as I said, geodesy today is probably the domain of geoscience which is the most multidisciplinary application, as I said, in many different areas. So try try to I would say try to address important scientific questions that are not yet answered. Look at emerging new research field, and try to do that during using different geodetic tools. Don't be, as I said just before, locked up in a narrow technique, but try to use different techniques to answer new question. New I can give the example, my own experience 20 years ago, about 20 years ago, when we started to use satellite altimetry to measure. Satellite altimetry has been developed to study the ocean, open ocean. That is, initially it was mostly devoted to measure the ocean circulation, and we we it was obvious that satellite altimetry could also be used to measure the water level change of rivers on land, lakes, etc. And we started to develop this domain. Now it's routinely done in many groups in the world. So this is my advice. Try to project yourself to new fields, new emerging fields, uh, because you know the technique, you know that you can combine different techniques to advance science in new research field. This is my own experience, and this is my main advice to the young generation, I would say. So develop multidisciplinarity. And this is very important because, of course, it's sometimes uncomfortable because you address new research field for which at the beginning you feel not very much expert, but you can collaborate with other communities. For example, in my case, I'm not. I have absolutely no background in oceanography, in climate research, but by you doing using uh, uh, space geodesic tools, I've been involved in climate research. I contributed to two as a lead author to two IPCC report and so on. So I think it's very challenging, sometimes uncomfortable, at least at the beginning, because you feel an expert, etc. But you bring new ideas, new views, new visions, and this finally it's very interesting.
Wonderful, wonderful. Yes, I do agree. I do agree. Professor, how do you see the development of this subject in 20 years, 10 years?
It's difficult to project in the future, but I think that we we can give a number of examples of at least for the next decade. I don't know if I can project in 20 years, but for example, I can just give an example I have in mind. To me, the space gravimetry mission, GRACE and GRACE follow-on, are probably the most revolutionary mission in space geodesy for the last 20 years. Because this technique is able to address important scientific questions in a large number of areas in earth science. As you know, water resources, melting of the ice sheet, mountain glaciers, change in ocean mass, uh, and even on the internal structure of the Earth through post-glacial rebound. So the response of the mantle to past and ongoing land ice melt, etc., etc. I I think there are new ideas to improve, in particular, the ground resolution of this kind of mission, which is already limited to about 300 kilometers. Is not enough to address a number of important questions. So I know that there are some groups which are focusing on new technology in order to reach a much finer resolution, and this will help us to address several new questions. Like I mentioned extreme events, but with the new project in space gravimetry, I don't know if you are familiar with that, but there is a project called Magic, which is uh, currently under development at NASA in the US and inside the European Space Agency in Europe, and which will be two pairs of satellite orbiting in two different orbits, and this will considerably, with no technology on board. I will not go into the detail, and this will allow to get a much improved precision and improved resolution with a lot of different applications. Even one application, decreasing intensity of the hammock. So you know the circulation in the North Atlantic, which is supposed to shut down in a few, I don't know, we don't know, centuries, decades of centuries, with considerable impact on climate of Western Europe. And with GRACE, it will be possible to detect any change in this North Atlantic circulation. This is just an example with this new technology. And we can give other example of progress expected um, in the future. So I cannot say more because I really don't know. I would like to be there in 20 years to see what have been the progress. So, but I'm sure there will be a lot of progress. In climate research, we are currently with all satellites in orbit, not only geodetic satellite, but all kind of satellite. We are monitoring change in all compartments of the climate system. But what is important today in climate research is to to address the question of tipping points. I am sure you. So irreversible change in a number of parameter of the Earth system, like I just mentioned one, the circulation in the North Atlantic, accelerated melting of West Antarctica, change in the Amazon forest, etc. The climate scientists have defined a number of tipping elements in the climate systems that are susceptible um, to suffer some irreversible change. And with the space geodetic mission, it will be possible to really start to observe such irreversible change, which may have a big consequence in for society, obviously.
Professor, as the last question, what can we do so that the decision makers and the person that they are running the country, they can value geodesy more?
Just to explain them that to focus, to insist on societal impact of what we are observing, and in order that they took the right decision to either to mitigate or to adapt, and don't talk about the techniques. It's not their job; it's our job. But insist on, for example, for sea level, it's very easy because we regularly say to policymakers, to other kind of stakeholders, sea level is not only rising, but it is accelerating, and it will probably continue to accelerate in the future because we know what is the cause of this acceleration. It is an acceleration in the melting of Greenland and West Antarctica, etc. So it's easy to message to them on focusing on the impacts, not on on the observation, on etc., but on the impacts. I think it's my opinion.
Oh, yeah. Thank you for being with us in this interview, and I wish you good luck.
Thank you very much. Bye bye.
Bye.